That was very comprehensive and encouraging. All of us are looking forward to Semicon 2.0 and what kind of transformative effect it will have in the industry. With that, I'll move to Dr. Rawal, who's been at the forefront of IP development in strategic electronics. I think there is a lot of my personal view is there's a lot of investment that has gone behind IP development, and there is a lot of distinct manufacturing capabilities also that's been built in the Indian ecosystem. Can you throw us some light in terms of what are our key strengths there? What are the areas that we need to further develop IP on? And what are handoff points between the government labs like SSPL or DRDO and the industry in terms of handoff of IP into military grade high volume production?
Good evening to all. First of all, I would like to thank ELCINA for giving us this platform to speak about the technologies which we are working on since last 1 or 2 decades. And first of all, I would like to go to the slides of first 2 fellow panelists from Army. They have nicely explained what are the requirements which they are foreseeing for sensor technologies based on compound semiconductors, GaN, RF or quantum technologies. So I am very happy to tell you that realizing the importance of all these technologies, DRDO, particularly SSPL, Solid State Physics Laboratory, we started working on these technologies long back. And today we have matured to a certain level where we can say that technology readiness level of few of these critical technologies is around 6 or 7. So they are readily can be inducted into industry and used for the production, and we are looking for that. So I'll come one by one. So to start with the compound semiconductors, initially we started working on gallium arsenide and technology, and developed the technology based on MESFET and HEMTs. And today we have a foundry where we can give these MMICs for our strategic applications up to 40 gigahertz. And now looking at the importance of gallium nitride, we have graduated to gallium nitride technology, and today we have indigenously developed complete solution right from the material development to the product development, and we have a capability to develop these devices, indigenous devices with our own design IPs up to KU band. And we are working towards Ka band. Design IPs have already been developed, and initial our conventional TR module was having 8 to 9 MMICs, but now recently we have converted that into only 3 MMICs. So front end chip, which consists of low noise amplifier, power amplifier and mixture or processing units, all these have been converted into a single chip, that is called front end chip. Then all processing chips have been converted into a core chip, and then control electronics. So many of you would have seen that they are already displayed in the exhibition, and we have readily available these technologies in our foundry. And then one of the other thing which I would like to stress is if you look at silicon technology, the advancement have taken place because of process innovations. So process is very, very critical. But unlike silicon technology, in compound semiconductors, the advancement have taken place because of material innovation. So material is very, very critical. So unless you have a material technology, you cannot get into the advanced devices. So we have parallelly worked into material development also, and today we have our own material IPs in wide bandgap semiconductor, be it gallium nitride, be it indium phosphide, be it silicon carbide. And then another critical technology which I would like to stress here is IR sensor technology, where we have started working long back on all 3 windows, that is LWIR, MWIR and SWIR. And today I can proudly say that even material is not allowed, and a lot of import embargoes were there. So now we have our own material technology, and recently we have seen quite a good success in FPA. and our own MWIR and LWIR detectors are performing as per our requirement. And now recently we are coming up with the expression of interest, and we want to get into the industry. So in DRDO portal, very soon we are going to come up with the EOI and inviting industries to take up these technologies for production. And in IR technology particularly, material is itself is a technology. Then there are many sub-technologies other than detector fabrication. That is ROIC again is a technology. Then you have, because these materials are very low band gap materials. So you need to have a cooler technology. So we have JT cooler as well as Sterling cooler. And I am very happy to say that our friends from Army Base Workshop 509, they have imported thermal imagers where majority of their failures were coming up with the thermal imager failure. So they interacted with us, and now we have replaced their bad thermal imagers with our indigenous thermal imagers, and now they are able to repair their bad thermal imager within 2 to 3 months. Earlier, this cycle was more than a year. So they are very happy, and they have taken this complete technology to their army base workshop. Similarly, this JT cooler, I would like to share this news that worldwide supplier is SCD Israel. SCD Israel supplies, and recently we have developed our own JT cooler and transferred the technology to the Technocraft, one of the private industry, which has developed this and qualified the JT cooler, which is used in these MWIR DDCAs for missile guidance. And I am very happy to say that we have received first order from SCD Israel for these thermal imagers. So now we are exporting these coolers to Israel also. And coming to the photonic devices, laser diodes are one of the very, very critical components. So we have our own technology. We have developed near IR laser diode based on gallium arsenide, and even single emitter diode of 10 watt is available at 976 nanometer. And recently we have also developed blue-green laser diode with 450 and 480 nanometer, and these technologies are now available for the industry take-up. So we are very soon we are coming up with the expression of interest on DRDO portal, inviting industries to take these technologies for civilian as well as military products. And then other technologies which I would like to stress is there are acoustic emission sensors which we have developed for landslide and avalanche snow detection, and develop the products with the industry partners, and those technologies are also available. And then for chemical, biological, nuclear warfare agent detection, surface acoustic wave sensor technology have been developed, and we have now transferred that technology to Bell, and Bell is now doing these e-Nasika production is being done by Bell. And then as my friends have already stressed the importance of quantum sensor. So recently we have started quantum sensor development also, and particularly we are targeting atomic magnetometer and atomic clock. But before going into the complete product development, you need to have the component development. So we are starting with the component development, and we have initially started micro fabricated alkali vapor cell based on glass as well as silicon, and then VCSEL diodes are required for this. VCSEL also we have started developing, and first prototype we are expecting within end of this year, and by the end of 2 years we will be having our own indigenous magnetometer as well as atomic clock with the stability of 10 to the power minus 9 seconds. So projects are going on with the full flow, and then looking at the importance of terahertz technology, we have started working on terahertz detector and sources also, and mainly based on gallium arsenide. Low temperature gallium arsenide is used because of the very low minority carrier lifetime requirement. So we have recently demonstrated the terahertz source based on these low temperature gallium arsenide, giving us the power in from 1 to 4 terahertz to the order of 160 to 200 microwatt, and we are working towards improving that. So a lot of work is going on in these technologies, and we hope to meet the expectation of our forces in coming few years. And I would like to invite all the industries to interact more closely with us, because without industry, we cannot productionize. Our job is to develop these technologies, develop the product, prove the concept, and then industry should take it forward for the production. So without industry, we cannot be self-sufficient. Thank you very much.
Thank you, sir. Very articulate show of the depth that we have and the call to industry to act. But last but not the least, the industry participant, Mr. Vinod Yadav, your perspectives on our pathway to indigenization, specifically to critical technologies and sensors, and what do you say are important elements of the future roadmap?
Yeah. Hi, good evening to all. I thank first ELCINA for giving me the opportunity to speak here. I'm Vinod Yadav, and I'm from Tassel Weapons and Sensors Division. And in today's talk, I'll specifically focus on the type of strategic sensor technology which is on infrared sensors. Now, infrared sensors are widely deployed in all the electro-optic systems, what is used in the military. What makes it special, like while you have CMOS imaging sensors, they are commodity, they are dual use, it's easy to source them, and the cost is very low. When we talk about infrared detectors, we are talking about a very niche technology, very few players globally, and therefore the risk on supply chain, not allowing us to get those sensors. And that is where Dr. Rawal from SSPL, as he has put, it's heartening to know that a lot of work is being done on the sensor technology itself. Now let me start going a bit into history. When we started the electro-optic development, system development, sighting systems, when we started that around 14 to 15 years ago, most of the technology at a product, electro-optic product level itself in defense was imported. Slowly build to print started to happen, where on a foreign bill of material, you are just doing the screwdriver technology of assembling or putting it together. When we decided to get into this area, the choice was whether to tie up with some players globally and try to do the same screwdriver technology, repeat and supply and call it indigenous, or go our own development path. We chose the latter. We went with designing our own systems. And it took a few years. It took quite some investment on building up the facilities, the clean rooms, the assembly facilities for these electro-optic systems, and of course putting in a lot of engineering hours to design these electro-optic systems. So we started with the simple ones like weapon sight, and we went all the way going to the long-range surveillance systems. We have supplied hundreds of them to the armed forces now. These are long-range surveillance systems, talking about 35, 40 kilometers detection of vehicles. That's the kind of thing that we're talking about. And multispectral, you have visible, you have shortwave infrared, you have midwave infrared, all in a common system. So this is what we delivered, and we vertically kept on going upwards the value chain by putting in more R&D in other allied areas. For example, gyro stabilization. When you have a camera on an armored vehicle, it cannot be just, the image will be shaky, so you need gyro stabilization and something that survives the shock level when a tank fires. So doing those, so we spent our R&D on that, R&D efforts on that, and I'm proud to say that now we have our own indigenous sighting system, long-range electro-optic system. So we keep on going upwards the value chain, developing these products. Of course, these products utilize a lot of electronics apart from the sensors that we will touch upon. And we had our own challenges in this. And it's good to see that the ISM, a big part of the challenge is, of course, the semiconductors. So in 21, 22, we faced the semiconductor crisis of non-availability of chips. Thereafter, we had a material shortage in electro-optic. A very critical material is germanium for the optics portion. And there was an export control by China on germanium, and they mine 80% of it. and that is what put us into a spin. So it's good that we shifted to alternate material, of course, like chalcogenides, and changed our complete design, removing germanium from the equation. However, as I said, we kept going vertically upwards, and while the semiconductor problems, optics problems, that kept getting resolved, one thing that we did not do is getting into sensors so far. So while we kept going vertically upwards, when it going deep down into the sensor technology, we haven't done it so far. Now, why is that so? Like, having worked with the global detector providers in these various spectral bands, one thing that we realize is it's a different ball game. While you have the standard semiconductors where we are talking about volumes, where we are talking about nanometer scale, in infrared detectors specifically, we are talking about compound semiconductors. We are talking about, they don't require the nanometer scale technology for the readout IC, but the material fabrication itself, doing the hybridization with the ROIC, the bonding, doing the cryogenic cooling or integrating the cryogenic cooler. Now, they are quite involved technologies, and on top of that, it is not just about pioneering or doing it with one type of material. You have various types of material, and each company specializes into different type, like the global players. So it's quite difficult at this point in time to do it alone. Like, I'll give you an example of, say, France on exactly the same technology. Now, Linred is one of the companies which work in literally all the spectral band of sensors. Now, it started in 1986 with incubation. It started as an incubation from Cialetti, which is one of the research labs based out of Grenoble. And it's over a period of time that the technology matured, and the semiconductor, what is now Linred was earlier Sofradir, that got incubated. And over a period of time, they grew as a company. They kept working on the material technology. They focused on industrialization. You can do a good amount of R&D. You can come up with very good chips or very good prototypes. But to do it so at an industrial scale is where the challenge lies. And that is the challenge that we have to overcome if we want to go to that industrial scale. Today, just for reference, if you look at, these are financial published numbers. Linred does, last year they did 2,500 crore worth of business in, I'm converting to Indian rupees. 15% of that gets invested in R&D, which is around 350 crore in this year, gets spent in R&D for doing the next generation. From research of a material technology, of a new material or a pixel pitch, now you either look at new material technologies which are more sensitive or which are easier to produce, or you look at reducing the pixel pitch so that you can increase the resolution by building more images on the same wafer. So there is continuous work going in that direction, but that work is not like you decide and tomorrow you have the chip. From material to an industrial scale is a 6 to 7 years of process, from the research lab going to the series production to the industrialization to the mass manufacturing. And that's the kind of patience that is required, and it is cyclic. This cycle is self-sustainable, and whatever you get, you again invest it back in the R&D, and that is how the ecosystem would continue, or this space will sustain forever. It's not about doing one-time investment and expecting that something would happen. Today they export 80% of the chips what they manufacture outside of France. Another thing that France as a nation did, right? So you have a company which starts building something. Say a PSU starts building that I'll build a semiconductor or I'll build infrared detectors. Somebody else may come up say, oh, this guy is building, I'll also build one. What France did, you had 3 companies, you have Thales, you have Safran, these are all the big names. So you had 3 companies which were all building competing technologies on infrared detectors. The government decided to consolidate all of them together by saying that as a nation, we don't want three parallel efforts going in these technologies, for which they will end up competing with each other, and they will lose as a nation global at the global stage. So in 2018, they decided to consolidate it into one entity, and where all the detector technology got consolidated. So you have only one company now, Linred, doing detectors, and everybody buys from them. So this was a good example of how the government stepped in to make sure that companies don't spend their efforts building parallel things and the same things together and then fighting with each other and losing out on that. And that is how you have a focused effort by only one company, which does all the work. And probably that was the right decision to go. Today they are building at a very big scale. A slightly different example. By the way, on the ownership pattern, what they did is exactly 50% is held by one company like Safran, exactly 50% by Thales, so that you don't have the controlling stake issue or the conflict of interest. Why I'm bringing this, no affinity to France as such, but just to bring out that in order for the ecosystem to grow, somewhere the policy or the government policy also has to work in consonance. Another example is Israel, SCD, as we mentioned. Now, SCD, of course, in Israel, the technology drive comes due to the persistent conflict, and therefore the demand is where that brings in the demand. But there also the government did exactly that. You have 50% of the SED owned by Rafael, which is a private sector, a PSU there, and 50% exactly by Elbit, to make sure that they are not building competing technologies and cutting each other. And this is how I think when we have to go from an R&D scale at which we are right now on the sensor technology to an industrial scale, somewhere these policies and probably something different, slightly different than the ISM mechanism may be needed to address this, because volumes are low, it is very strategic, and as a nation we have to put all the efforts together to build one so that everybody could consume it. Otherwise you will have a situation where if it's a DPSC doing it, probably the private sector may not buy due to the competitive aspect. So these aspects should be kept in mind when we are trying to build in the sensor at the industrial scale that is needed. And yes, we agree that it is the need of the hour, because without it, these systems or thermal imagers or night fighting capabilities won't exist. That's it from my side. Thank you.
Thank you, Vinod. Any questions from the audience?
Sir, what is the subtle difference between photonics and quantum in your approach while working, sir?
Photonics devices are using optical properties, and quantum Hello? Yes. So, photonic devices are using optical properties, and signal processing is happening in the optical domain. Whereas in quantum, we are utilizing or exploiting the quantum effects for the sensors.
Quantum computing and all.
Quantum computing is different, but that also utilizes quantum effects. But sensing and computing both uses different aspects of the quantum technology.
Sir, you mentioned 99% accuracy. In the sense, we lose some features, or the effect will be on all of the features.
Which what accuracy?
99% accuracy. This are in your presentation. You have mentioned 99% accuracy with robos.
Oh, so that's the.
Will
end-
that be on all the features or some features?
No.
we
That
lose?
is okay. So that is actually, you can see it in YouTube. The Chinese factory put about 1,000 robotic workers, and they are manufacturing tablet 24/7. 6 days continuously they live streamed. 99% of their production was accurate, quality wise. That's what it means.
Thank you, sir. Thank you, sir.
Last question, maybe.
Sir, the sensors, earlier it was all analog sensors. Now it has shifted to digital sensors. So there is the sensor portion, the microcontroller or microprocessor portion, and the digital output. Can it be integrated on the same substrate so that the temperature variations equally distribute over all these different systems? And also we need to have sensor fusion and redundancy of sensors in all systems, so that if there is a sensor failure, the other sensor takes over and there is no loss of signal from that particular location. Is this addressed in sensors development in future?
In sensor technology, because there are various sensor technologies, but if you take the example of photonic integrated circuits, so if you want to enhance your present technology to the newer levels, you need to have the advanced packaging and integrating technology, which are still in the nascent stage. People are developing those. Once you establish those packaging and integrating strategies, you can have what you are mentioning. All those things can be achievable.
Because most of the sensors are non-linear. After a certain, they saturate. So linearity also should be addressed so that
when you are
the output
processing
is
signal in
linear.
optical domain, all those things are not going to matter much. So it's a matter of how you are processing the signal.
Thank you for the question. I think
Thank
we
you.
are. Thanks a lot for the entire panel. Enriching conversation on, but lots to do. I think we are at stage 0, lots to do, and maybe Rajuji next SES, let's dipstick of the level of progress we make as an ecosystem. Thank you.
Ladies and gentlemen, let's give a huge round of applause for our moderator, for our panelists, for a thought-provoking session. Thank you so much. May I now request Mr. N. Ramachandran, Executive Chairman, MEL Systems and Services and past President, ELCINA, to please join us on the stage to hand over the memento as a token of gratitude and appreciation. Mr. Sudheer Narayan, partner, Bain and Company. Let's give him a warm round of applause, everybody together. Thank you for sharing your thoughts on strategic electronic sensors and critical futuristic technologies. Colonel Anupam Tiwari, PhD, from 515 Army Base Workshop. Colonel Premnath Othayoth, SM, from 515 Army Base Workshop. Dr. D.S. Rawal, Associate Director and OS, SSPL, DRDO. Mr. Vinod Yadav, Vice President, Design, Tata Advanced Systems. Mr. Sarin Sundar, CTO, India Semiconductor Mission, Equipment and R&D. Can we all come together for the group photograph? We have a quick announcement by Captain Sanjay Sharma, and I request everybody to stay back.
Ladies and gentlemen, flash message from the Chief of the Naval Staff. As I had the privilege and pleasure to speak on behalf of the Indian Navy on the indigenous efforts. So I'll request the panel to please allow me to felicitate the ELCINA organizers. I'll request you to sit down, please. So please take a seat. Okay. So may I first request President ELCINA to kindly come onto the stage. I'll request Colonel Anupam Tiwari to present this memento on behalf of the Chief of the Naval Staff to President ELCINA. Now may I request the Karta Dharta Secretary General of ELCINA, Mr. Raju Goyal, to kindly come to the stage. I'm sorry I'm troubling you. I know you have a issue. May I request Colonel Premnath to kindly come forward and present this memento on behalf of the Chief of the Naval Staff. So this was last minute, and I stand guilty of troubling the organizers, Raju ji in particular. Now may I request Miss Tina Burman to kindly come to the stage. Come Tina, don't worry. I'm not going to shoot you. May I request the chair of this session, Mr. Sudheer Narayan, to kindly present this memento to one of the main person who felicitated these presentations. Thank you, Tina. I'm sorry, this was a last moment instruction. So now one of the persons who helped me in the presentation was Mr. Joshua. May I request Mr. Joshua to please come to the stage. May I request the gentleman from Tata Advanced Systems Limited, Mr. Yadav, to do the honors on behalf of the Chief of the Naval Staff. Thank you so much. And lastly, but not the least, Mr. Prem Kumar, is he here? Mr. Prem is not here, so whom can I ask from ELCINA to come? Okay, I'll ask our charming, graceful lady. Please come. May I request Dr. Rawal? Is he here? He's left already. I guess Mr. Sundar Sareen, the CTO from the semiconductor mission, to kindly do the honors. This is for Mr. Prem Kumar. On behalf of him, I have requested this lady to receive the small gift. With this, I conclude the small impromptu ceremony. And let's, ladies and gentlemen, give a big hand to ELCINA for this marvelous and nation-building effort, which I wish continued successes in the decades to come. Thank you very much. Jai Hind.
Ladies and gentlemen, as we come to the close of day 2 of the 15th Strategic Electronics Summit 2026, it's my privilege once again to extend our sincere gratitude to all our distinguished speakers, session chairs, panelists, delegates, partners, exhibitors, and participants for making today's deliberations insightful and engaging. Your valuable contributions, thought-provoking discussions, and active participation have truly enriched the summit. With that, we conclude the proceedings of the Bharat Security Expo, co-located with the Strategic Electronics Summit 2026. We wish you a safe journey home, and we look forward to meeting you again at future ELCINA events. Thank you, have a wonderful evening, and Jai Hind.